Hello, welcome to Engineers Ireland and to the Leaving Cert Maths Grounds. Today we're going to look at the Project Maths approach to trigonometry. The easiest way to understand the approach is really to look at the questions that have been asked already, and that's what we're going to do. As you know, at this stage there are two types of questions on Project Maths papers. There are short ones, which are of modest enough marks, such as the one you see on the screen here, 25 marks. And then they're generally questions 5, but it can be located differently in the paper. So don't worry about it being specifically 5. And question 8 usually is the big trigonometry one, which is worth something like 75. So then, what kind of stuff are they asking? They wish to know if you have a clear understanding of how things relate to each other. And once you get your head around that, you'll find that this is much easier to deal with than the previous maths course. So let's look here. The first part of this, part A, is actually quite simple. And we'll do it as a little aside later on, because the main thing I want to look at, and in this question, is this part B bit. They've given 3 functions. They're drawn here, and obviously they've been named f, g and h. They've labelled the x-axis in tick marks and the y-axis in tick marks. We're told what these 3 functions are, and we're supposed to go along and identify which is which. In other words, is f of x the cos 3x or the 2 cos 3x or what? What is it? And put the answers in the spaces. So, the important thing to recognize is anything multiplied by 1 is unaltered, so I can multiply a 1 in front of the cos 3x. And now what we have are 3 functions. One of them is a trigonometric function multiplied by 1. The other one multiplied by 2, and the other one multiplied by 3. What do they relate to? The small circle on the inside here has a small radius. The larger one, the largest one, you can see can extend all the way up here, all the way down to here. So from a viewpoint of a circle and finding what trigonometry means in relation to it, let's come over here now and draw our circle, our big circle first. Then we'll draw a second one, and then we'll draw a third one. What we're saying is that if I pick a radius, and we will look at it from the largest circle, because it'll be the easiest one to draw stuff for, and we say, I'm looking at its radius, and we'll just call it r at the moment, and we'll say, we're looking for how big that line is, and how big that line is. What do we know about these things? We know that if we had a unit circle, that cos's and sines fluctuate between 1 and -1. Whereas when we have a radius r, you will find that the vertical distance, like this one here, is going to be larger than just if you had a radius of 1. And we'll just say, for argument's sake, we'll call this x, the angle. We know that that side there is r sine x, and we know that this side here is r cos x. if I would draw another drawing for you, you will understand it perhaps a bit better. Look at the unit circle, first quadrant of it. I pick any angle. We know the radius is 1 because it goes to a maximum of 1 no matter where you go. This we know is sine of the angle, which we can call x, and this length we know is cos of the angle. If now we extend out our radius to r, and we're now looking for this vertical length here, what do we know? We have two triangles. We have this small one here, and we've got the larger one. They're similar because they both have right angles. They both include the angle x, so the third angle must be the same. Therefore they're similar, and they must hold ratios in relation to equivalent sides. What do we know on this one? The big side, the hypotenuse here is r, and on the small one it's 1. So the ratio is 1 is to r. And equivalent sides will have equivalent relationships. So this side must be r times bigger than that side. And this one, all the way out along here, must be r times bigger than cos. Now go back to this other drawing. As this radius starts to move, you will notice the sine is getting bigger, and it'll get to its maximum here. So we can see the peak of sine functions or cos functions is related to the radius. So the height here is a measure of the length of the radius from the circle that produced this particular sine function or cos function. So which one are we dealing with? Is it a sine function or is it a cos function? You can see it immediately from any of these drawings. For example, when the radius lies flat along the x-axis, the angle is 0, and you can see the cos is equal to the radius. So for 0 of an angle, you have a full radius in height. So because we're over here at the xy axis, and at 0, 0, the origin, and all of these functions have their peak for 0 angle, these must be cos's. And as you can see here, they are cos's. We know our radius for the big one is 3, so that's a 3. For the next one it's 2, this is a 2, and for the last one it's just 1 unit. And equivalently we can write down here. So that's the y-axis labelled. We also know what the functions are. The one with that reaches the greatest height has the biggest number on it. So looking at them here, we're told this one here is f of x, and we can say that's 3 cos of 2x. The middle-sized one we're told is g of x, and that must be 2 cos 3x. And this must be the smallest. Now we're looking for a labelling of, or putting a number on the tick marks on the axis. That's where we have to start focusing in on this bit. So angles. We have 3x, we have a 3x, and we have a 2x. What does that do? If we just had a cos of theta, how does it relate to a cos of 2 theta or a cos of 3 theta? Let's look at a little circle again. And we'll just pick the unit circle. And we'll pick this angle here. Sin x cos x. So if I plot x, the angle, against its sine and cos, I get the standard sine and cos functions. But what would happen if instead, even though I'm looking at the angle x, I'm going to double it in size, so that this angle is now 2x. And I'm saying that even though the angle I'm going to plot on the x-axis is going to be x, just the simple angle, I'm going to be plotting it against the cos of double of the angle. So while we do know that that line is the cos of x, what we're now finding out is that that length is the cos of 2x. Now, what you can see is when this angle reaches 45, the blue one has already reached 90 degrees. It's vertical. While my angle, the x angle, travels all the way to 180, which will be all the way around to here. When x gets to 180, the blue one, which is 2x, will have already completed the circle. And we're plotting x, the angle x, against the cos of twice the x. So by the time the angle x has travelled from 0 through 90 to 180, it has been plotted against angles that have gone from the cos of 0 all the way through to the cos of 360. That means it's got to plot the whole fundamental shape in half the length of the angle that it normally would be if it was related to itself. If we pick this big one, what we notice about it is that when we have just drawn this much of it, it's now beginning to repeat. This is just repeating what happened over here. So that's the full shape. The highlighted one here is the full shape for cos. We know that those cos angles have been produced while our angle, in the case of this lad here, because we've been looking at the 2x one, while our angle is travelling to 180, we've got the cos of everything up to 360. If we're looking at 3x, in other words, cos related to, or sorry, cos of 3x related to x, if we're doing that, we know that while I'll have gone only 120 degrees, 3 times 120 is 360, so I've got the cos worked out at that. Of the 3 of them, this one, because look at the 2 here, it's 360 over 2, which is 180. This one here, it's 360 over 3, which is 120, and the same is true for that one. it takes x to travel 120 degrees to get all of the angles from a circle when you have got you're dealing with cos of 3x, and it takes it 180 degrees to travel to get all of the angles when you're dealing with 2x. So of these three, the one that took longest in this direction to complete this whole shape is the one that belongs to this, the 2x, and we know it's 180 degrees, which is pi. We also know that these other two, for example this one, will complete the shape again. It finishes there. That must be 120. Which is 2 pi divided by 3. And it's easy enough then to work out what each of the other major locations are. Here, here, here. It's the same basic process. You're just going a quarter back the way or doubling up the way, and you find them. The trick is to find the angle belonging to the completing of the shape. In this case, for the 2x's, it was 180 degrees. The shape got completed here in 120 degrees for the 3x ones. A little point arises now from this. Yes, we're working out the axis. How many points should you actually be showing on the axis? Is it every place that these things are crossing the x-axis, or are we still just supposed to use an ordinary set? Now, as far as I can see, these guys have only put one tick here and another tick here. And this should be 2 pi, which is 360. And even though we can work out all of these other locations, I don't believe we've been asked to do that. We were just asked to label the axes. So our life now gets easier. We shouldn't have any more than that to do here, because we weren't asked for more than that. Okay. This has been deliberately very chatty or wordy. Okay, we could have dealt with this much faster if we looked at it from maths equation side. But it's still no harm to remind yourself every now and then that actually all you're dealing with is a circle when you're dealing with sines and coses. And the amount of swing, as in how high it can get, tells you what the radius is. Similarly, that distance is minus r. So if that's going from 0 up to 1, and if you have a radius of 3, you would expect the peaks to go that high. See, like this. If that's 1, you'd expect 5 to do something like this. It's a simple scale thing. So the radius of a circle is simply multiplying a scale into a standard trigonometry function. When you're looking at it in terms of how long does it take to complete things, if we've got a cos or a sine of, let's say, n theta, how long does it take to complete the basic shape the sine shape or the cos shape, it's going to be 360 over n. If we had cos of 4 theta, we expect that by the time our theta has moved 360 over 4, which is 90 degrees, that the function will have completed its cycle. And once again, just in case you're not clear, this shape here to there is the complete cos shape, and it's almost exactly the same as the sine shape. It's just that it's been moved 90 degrees. Little part A of this question is quite easy. This piece here. It's saying solve this equation. Cos of 3 theta equal to a half. First thing you should notice, like in almost anything you would do in algebra or any other part of maths, is you check to see what the sign is. It's a plus sign. If we look at a circle, we know everything is plus here. I like to go the reverse way around because acts, as in acts in a play, sticks in my mind. So everything is positive here and cos is positive here. So we know that the only type of answers that will come out of this question are related to quadrant 1 and quadrant 4. What shape should we have for it? Well, if we have a particular, I don't know how that happened. Doesn't look as good now. If we have a particular angle theta, the R angle down here, which is a theta, these give the same cos. First quadrant in a solution from here is just the angle itself, theta. The one down here, though, is 360 minus theta. So the angle up here is the one you go for first, always the first quadrant. What angle gives us a cos of a half? It's 60 degrees. Now, do you notice anything? Because in an exam, this is how your mind is likely to be thinking. You're working through this. You should not lose sight of what the question asked you. Theta is in radians. You can work all the way through on degrees if you wish, but at least convert at the end. So we're saying 3 theta is 60, and 60 is pi over 3. So we're happy that in the first quadrant this will be our solution. In the fourth quadrant, this is the type of thing we're dealing with. So is that how it works? in an exam you're going to get a little nervous and you'll be looking at it and you're saying, is this what I'm supposed to be doing here? Is that how it works? It's amazing, but probably for 4 years in secondary school you'll have been dealing with basic trigonometry. But in an exam, it's terribly easy to actually get things wrong. What is the solution here? It's 360 minus the 60, which is 300, is equal to 3 theta, which implies theta equals 100. But we've been asked for radians. That's not clear. Pi over 6, which is equal to the 3 theta, and you get your theta from it. These questions are actually very easy, and that's why I'm using this as the one to just remind you of how easy it is to stop being relaxed in the exam. And it is possible to be relaxed in the exam. Once you start to get a bit nervous, what you find is that even basic little things like what we were doing over here, you start to doubt them. It's very important that you don't let that process take over when you're in an exam. Now, I imagine that, like almost every other person in their teens that I know, you have a strong interest in music. And believe it or not, there is an aspect to it that is very helpful for you. Music has a beat. What you've got to do is, or one particular solution for you, is to keep a slow beat in your mind. If you do so, what you will find is that even when you start to panic a little, you can always return your mind to hear the very slow beat, and you hold with it. You don't let your mind run off and start to panic. It's really important that you keep It's very important that you keep a calm mind in the exam. Even when you write an equation the wrong ways around, look at it carefully, ask yourself basic little questions, stay calm and straighten it out. There are more marks to be lost in bad management in the exam than possibly being gained between now and the Leaving Cert in good study. So improve your exam craft by remaining calm. Let's look at this particular question. Now, it's from a paper that got withdrawn by the department after they had released it, but there's still nice and useful things in here. Now, by the way, that's cos squared. We're asked to show that that equation may be written as a quadratic. Okay, it's not a difficult thing. What you will notice is we have two functions, cos and sine. And the cos is squared, and we do know that cos squared plus sine squared is equal to 1. And very quickly, you would realize that that is the secret way out of this. And in particular, they're telling us, oh, we want a quadratic in sine. That's telling you, find a means of translating cos into sine. and that is a quadratic. So, part A, that's the end of your part A. Show that it's a quadratic. Next, you're asked to solve it. Well, you should know that maths can often seem a lot easier if you name things. In our minds, we can call this anything we like. You could call it y. You can name it as anything. But you just see it, rather than being a function, just see it as a name and something that you can play around with by way of a name. So, what can you do with that? You look to factorize it. It's the same as having an ax squared plus bx plus c. Can we factorize this? This tells us that one of the solutions to this is negative and the other one is positive. The positive one wins out the battle when you add them. We have another step to go, because we've been asked to find for the values of x in the range of 0 to 360 degrees. This time it's not radians like the last time, so you can work in your more familiar degrees. We've got the same problem. First off, identify where is sign negative in this case, and over here where is sign positive. The same little drawing will show us again. A, C, T, S. All and sign. Sign is positive here and all are positive here. So the solution to this piece here is going to come from quadrant 1 and quadrant 2, and the negative ones are going to come from here. And it's solved the exactly same way as the previous one that we looked at. I'm hoping you can see at this stage that these are very doable questions. The important thing is just that you understand your maths. You understand it primarily, especially trigonometry, by drawing drawings. I'm constantly drawing these little things because I don't leave it to my mind to visualize what quadrants or anything. Draw a little drawing, see it, ask yourself basic questions about it, and come back to your problem again, because then you're clear in your mind. Okay. Wait to see how easy this is. We have a function. What have we learned so far? The number multiplying into the trigonometric function is the radius of a circle. So the solutions from this function belong to the surface of, or the curved line that is this circle of radius 3. We're looking for a sine function, and it is of x relating to the sine of a 2x. remember what we found out? That the 2 in here, you will go 360, which is the normal full thing to get all of the trigonometric function values off a circle. But we're going to divide it by 2 and say this will now all happen in 180 degrees, which is the same as 2 pi over 2, which is pi. All of the sine will play out in that space. We're asked to complete the table below. Well, when we know x, it's easy enough to know what 2 x's are. Sine of 2x. The sine of 0 degrees is 0. The sine of pi over 2 is 1. The sine of pi minus 1, 0. 3 times it. Okay, now you're asked to graph this. And that basically means this value along the x versus its equivalent value along the y. These points will be easy, but it's important to try and draw a decent graph while you're at it too. So we get 0, 0. We will get, for pi over 4, we're going to get 3. And we might as well label this thing. I have a habit of labeling the vertical axis on its left hand side over here rather than over here, because when you get down to the negative ones, you would be writing something like minus 2 here, and your eye notices the minus sign. But look at up here, the 2 behind the tick mark can often look like a minus, and it's a little confusing or can slow you down. Put it to the left hand side and it'll be okay. So then, this one should sit here, belongs to this. Back at good old pi over 2 again, it's back down to 0. It heads off down to 3 here, minus 3, and it comes back up here. You can, if you want to, but don't, think in terms of drawing your graph in straight line bits, because you know that's not the shape of what sine is or cos is. They actually have a characteristic shape, and you should at least try to include that shape. So what do you know from your calculus, and even also from just looking at your functions? You know that it actually remains horizontal for a while at the peak and horizontal for a while at the base. We know that the angle coming from here then won't shoot for that point. It's going to shoot for something over here a bit. The line does cut through here. Now this downslope here should be the negative of this upslope that we have there. Again, you want to aim away from this point. Now please understand that it's very difficult to draw curves or even write on this screen. It's much easier for you to do it on paper with a good pen or pencil. So you should be able to do much better than this. However, even as it stands, that's good enough to show itself to be a sine curve. Whereas if you had done that, that does not look like a sine curve. So at least make an attempt to make it look right. Well, that's that question. Look at this 25 mark question. Straightforward stuff. Triangle ABC. D is a point along BC. The lengths AB, AD, AC and BD are as shown. So you're given all of that information. You're asked to find the length D to C. Oops. That length. So what do you know about solving these problems from Junior Cert? If there's not enough information in the triangle that you want, and it would have to be this triangle that you're really looking for because this side belongs to it, you find a triangle that has at least 3 pieces of information. We are fortunate that we have all 3 sides on this one. As a general rule, if you're looking to decide whether you use a sine rule or a cosine rule, if you have a side and the angle that's opposite it, you should be looking to use sine because it's an easier function. Whereas here, what we have are 3 sides and no angle. So what angle should we go for? Well, we do know that all of this is 180. So if we find out that angle, it will let us work out this one. That makes this angle A and this side A for a cosine rule. And the other two, it makes a little difference whether you call them B or C. What else do you know? Those 2 sides are equal, so it's also telling us something about this angle here and that angle here, and you have to decide whether or not it's relevant or whether you should go straight on to the cosine rule. With a cosine rule, you will find that cos of your angle (53.3) approximately. That means this one approximately. Is that correct? Well, no, it's not. So what do you get from this? Is that correct? What do we do with the second triangle? We are looking for this, aren't we? We now have one side here that we know. We have a side here that we know. And we have this angle here that we know. What can you do? Well, you can either at this stage use a cosine rule, or you can successively use the sine rule twice to solve the problem. It's very straightforward. so far, nothing that's been asked could be considered difficult for you. You've been well trained beyond this point. So now, let's see, and these, remember, are just the 25 mark questions. So it isn't surprising they should be well inside your ability. So let's look at this. Again, 3 triangles, and you're asked to express cos alpha and cos beta in terms of the labelled lengths, and to prove this, to prove that that is so. Do you notice it's looking for cos and cos? So it's screaming out to you to use the cosine rule. What do you do now? How do you connect this information together? What's the connect? What lets you go from having worked these two things out to being able to start establishing a single relationship? Well, it's the exact same thing we saw in the first half of this question. This angle here is all 180. So beta is equal to 180 minus alpha, or vice versa. We've just subbed it in here now for the beta. What's cos of 180 minus alpha? Rather than going through your trigonometric identities, it's much better to draw your basic little drawing again, your unit circle, and ask yourself, let's say this is alpha. What's 180 minus alpha? Well, all of that is clearly 180. So we'll find something like this is 180 minus alpha. Now, let's look at these. The sign is definitely still positive in both of these. We're looking for a cos. The cos is, if drawn correctly, is of equal length. The only thing is this one is negative. Is that correct? Or is this correct? Just look at your little diagram. We are over here looking at cos of alpha, and this one is minus it, so it's minus cos of alpha. So we have, and we know that this is minus cos of alpha and this is cos of alpha, so that lets us put the two together. And now you're just involved in a little multiplying back and over. If we multiply everything by everything that shows up in the denominators. There's a 2, there's a P, there's a D, and there's a Q. So we're going to multiply across by 2PDQ. That will imply that I'm going to get a Q outside of and you get to an answer. They're all the short questions. Now you're looking at ones that are worth 3 times the marks. What do you think will happen? What used to happen in the honours maths, in part C's, it would be deliberately complicated up very often by bringing in constants that you didn't know, and therefore you're bringing in a lot more algebra in sections such as trigonometry or vectors or whatever it is. And it was designed to complicate your life. So far, it seems that that's not what is taking place in project maths. What's happening is they're looking to see if you can pick out the information that's necessary to solve a problem. And what that basically means is that now you may get more information than you need, and your job is to be able to set stuff aside and say, I don't require it, and you work with the reduced set. That was not the case before. Look at this problem. A tower that is part of a hotel has a square base of sides 4 meters and a roof in the form of a pyramid. The owner plans to cover the roof with copper. To find the amount of copper needed, they need to know the total area of the roof. Straightforward, sounds practical problem. A surveyor stands 10 meters from the tower, measured horizontally. Because what you can see is there's no way the ground that he's standing on at the moment is at the same elevation as this ground. Almost everything you've covered before, for example, would be dealing with triangles like this, and you'd be looking at the height of a pole or a gable of a house or whatever it is, and it was given that these were all on the same level. That's not the case here, so be careful. What you will notice is that the surveyor is peeping through an instrument which has a tripod under it. So the level at which he's looking at is not even the ground level where he is. It's a bit above that. It's maybe 1.5 meters above that. What we're now finding out is we have a distance. That horizontal distance we know is 10 meters. See? But it's the horizontal one, okay? It's not that distance down to here. We find out 3 things. The surveyor takes 3 readings. He finds that he's got an angle 46 degrees to the top of the roof. He's got an angle 42 degrees to the base of the roof, to this point. And he's got an angle of depression, in other words, a down angle of 9 degrees here. That's to get you to the ground level, up the tower. We're asked to find the vertical height of the roof. Think about it. You're being asked for this question. You're not being asked for that. And that's important because it allows us to throw out one piece of information. What's the next thing they're going to look for? Find the total area of the roof. Again, that doesn't require information and down here. And if all of the angles observed are subject, blah blah, you will find that again we need nothing about this down here. We're going to do all our work from that line here. And that is a horizontal line, and we're back to our good old-fashioned problems like this with a horizontal base. By simply dismissing everything below that horizontal line. So you've been given more information than you needed. We're in familiar territory though now at this stage. We've two triangles. A smaller one that is only a 10-meter base, but the upper triangle, as you know, has the whole 10 meters plus another 2 out to here. So a 12-meter base on that one. The height we are looking for here is clearly the difference between that height and that height. Have we been given dimensions? See? So the answer to that is meters. That's the height of the roof. But the problem doesn't stop there, because we have to now recognize that we have a little visual problem to solve. Let's draw what the roof looks like. That's just a horizontal line for convenience. I want to form a square base. Now, having formed the square base, we know the sides are 4 meters by 4 meters, and let's just find the middle of it. approximately. Because we know the top of this regular pyramid will be directly above that middle point. That's what the roof looks like. What have we worked out? We've worked out that height there. We know it's 3.43 meters. But there's 4 triangles making up this roof, and each of them are sloped. They're sloped into a point like this, and we know the vertical height. What we have to work out is that. We don't know that height. What length is that? We'll just call it L for the moment. What length is it from the peak to there? Well, you should be able to see that we have a triangle formed now. And let's draw it on its own down here to keep our life easy. .43 meters in height. Each of these little base, half the length of the base things, they're 2 meters. So now we'll be able to work out what L is. So we know 2 things about our triangle, about each of our triangles. We now have the height. We know the base is 4 meters. The height is that value here. Area of a triangle. It's half 4 by 3.43. And when you work that out, you might think you solved the problem. You haven't. It has asked you find the total area of the roof. There are 4 of these. There's the one we're looking at here, that whole side. There's the one at the back. There's the one at the back there, and there's this big front one here. There are 4 sides to this, so the answer gets multiplied by 4. And it's square meters because areas are square and because we were given a dimension. Now I didn't spot that it has asked anywhere to the nearest to 3 significant figures or anything like that, but that's accurate enough. Your calculator will give you more numbers than that. If you want to put them in, put them in. But you're showing that you know how to solve the problem. The important thing that you should learn from here is bits of information such as that sloped line down the way. That extra piece of tower height here is irrelevant to us solving problems with this up here. Right then. There's one last piece. Remember, this is worth 75 points. That's serious money. It's worth your while to spend time on this and to do it carefully, because if you don't make mistakes, whatever you've learned you'll be able to use and optimize, and you will do better than somebody who may have started with more information and just wasted marks through simply by not being careful. Okay, what's the last piece here? We have already worked out the vertical height. We also have worked out the area of it. It's saying if all the angles And this is the bit that you really have to think about. It's not beyond you, it's just a different thought. That's all it is. If all of the angles observed are subject to a possible error of plus or minus 1 degree, find the range of possible areas of the roof. Well, again, a simple drawing will solve this for you. If we look at the situation, we managed to work out that height based on 46 degrees, this one having been and the blue one being 42. What would make this height bigger? Well, if the red line pushed up a bit, it would get bigger, wouldn't it? So if 46 degrees had 1 degree, because remember it's saying plus or minus 1 degree, if it had 1 degree added to it, you'd be getting 47 degrees, and that would certainly be giving you a bigger height here. So that's going towards the max, the biggest one. What else would make the vertical height here bigger? If this dropped here, that means that if that line drops, if the blue line goes down, if it swings down, what will do that? If this angle here, 42, has 1 degree taken away from it, you'll get 41 degrees. That height we're looking at here is based on 47 degrees and 41 degrees. That'll give you the biggest height, therefore the biggest area. So solve for the area. You just repeat the steps that you did before, work out the vertical height, then work out the sloped height of one of the sides, and then work out the area of the triangle and multiply it by 4, and you've got a max. So what makes things small now is what we have to work out here. Again, the vertical height is worked out by the two angles, by this angle and the one causing this. That vertical height, if it became smaller, if it dropped down to here, you would get a smaller area for the roof. So that would be when 46 has 1 degree taken from it. If the base pushes up, we have now finished up with a very small vertical height to the roof. What causes that? If the 42 has 1 degree added to it. Now, using those two, we're going to be working out that small height here. So, work out the height, get the sloped height of one of the sides, find its area and multiply by 4. Do you notice that in this part 3, not only is the mathematics not any more difficult than the first two parts, but we're even repeating the process. The real issue, though, is you did have to think about it. What do they mean here? It is much easier to think when your mind is as calm as you can have it in the exam. It is very important for you to find some method that allows you stop the mind from running off and getting all excited when it sees things like this. One of the easiest things I find for these things is that whatever it is to do with trigonometry or almost anything else, it's almost always possible to draw a drawing. draw a little drawing. You noticed when we had our square-based pyramid, with that vertical height, there's a lot of detail in that drawing, and having worked out our vertical height, we were now considering the problem of that length, remember? The sloped height of a side. And we recognize that we have formed a triangle. Now we have even more information in that drawing. What do? You redraw the bit that matters to you. This side is this sloped side. This side is the same vertical side, and this side is there. It does clarify things to make an extra drawing or an extra two drawings. It also helps you get your thoughts out rather than trying to imagine it and visualize in your mind and wear yourself down. Now then, I think this is the last one we have. Oh no, we have another little piece. Question 8, another 75 marker. A stand is being used to prop up a portable solar panel. And just in case you didn't know what a solar panel was, they're showing you. Oops, come back here. It consists of a support that is hinged, see, a hinge, near the top, not at the top, and an adjustable strap. Here's the strap going from there to there, and you can see there's a bit left over here so that you can extend it. Okay. And what we're looking at is a side view of this. Okay. It's saying by adjusting the length of the strap, by letting some of this in or pulling some of it back out again, the angle between the panel and the ground can be changed. That's pretty obvious. If we pull the strap back in this direction, it'll send this up this way and it'll become more vertical. And vice versa. We're given dimensions. We're told AB from A up to B is 30 centimeters. Centimeters. We have dimensions. We must give our answers with dimensions. We don't get all the marks. So we should take a serious note. I have a habit of marking a dimension on the question itself, just so that I don't forget towards the end of the question. So that's 30. We're also told that A to D, which is the same as C to B, is 5. So we've got 5 here. Centimeters, of course. And we've got 5 here. and that leaves 20 in here. C to F. Is 22 centimeters, and E to F is 4. Probably the most important thing for you is to again recognize the point that was made in the last one, that you are not as likely to encounter parallel lines in these problems as you would in the traditional maths course. Just because this looks to be almost parallel to that doesn't make it parallel to it. You cannot make that assumption. You will be wrong if you make that assumption. So don't automatically start to think that this triangle is similar to the larger triangle ACF. It's not, because that is not parallel to that. If you do not make that assumption, this is quite an easy problem. If you make the assumption, you're going to be wrong from the start, and you're likely to get a significant cut in your marks. Find the length of the strap DE such that the angle alpha, this guy here, between the panel and the ground is 60 degrees. That's a nice little trigonometry problem. How long does that need to be, that strap there? What length should it be to give you 60 degrees there? So what you do is you assume it to be 60 and you look to see what your dimensions tell you. We're looking for D to E. Now you can always name things. Now, just to be clear, angle X is not necessarily the same as that angle, okay? So you want to stick, when you're working out your Y and your X, you're going to stick to the big triangle. You will not move into the small triangle on this one. So that means the angle A up to C and down to F, that implies, which we've named Y. It's 180 minus, and we already knew we had a 60 down here, and minus 79.77 degrees. So we've got our angles. Particularly, we went for this angle just because it was an easy one to find out. We knew a number of things, important things about it. We knew the side that was across from it, so we were forced to use it. But what we were looking for all along was that one. This now gives us an opportunity. The opportunity is we have that length. 18 centimeters. It's the 22 minus the 4. We also know that length, it's 20 centimeters. So we've two lengths. We have that angle. Notice we do not have a length opposite an angle. So how do we find it? Cosine rule, sine rule. Which? It has to be the cosine rule, because how you know you can use the sine rule is you must have a side, an angle, and the side opposite it. And cos of the y, which is what we've worked out there. .2 centimeters. Don't forget the centimeters. That was easy, okay? What you needed to do was to avoid thinking that that was parallel to that, and you can see the maths you've been using is actually junior cert maths. There's nothing difficult in this other than calm, patient thinking. What else are they looking for here? Now this is where life gets interesting. Find the maximum possible value of alpha correct to the nearest degree. Well, we could, for argument's sake, get it to stand vertical. And you might argue, well, that's alpha equal to 90 degrees. But you're supposed to recognize that that's not what you're being asked. Because if you do that, you don't now have a support. All you will have is everything standing vertical. You're looking for the biggest possible angle of alpha that still keeps a support for the panels. So how does it work? We can see that as this starts to move over here, this will get pulled in. What's the limiting condition? We don't even have to change that diagram. This is probably the best way to show it to you. There's a hinge here. That means this thing can swing backwards or forwards. If we look at that as being a radius, we can now recognize that the end of that radius will fall onto this curve here. Once you've passed this point here, we're saying that this will be off the ground. Let's pick that point here. It'll miss the ground. Now, we do understand that that is moving at the same time, but we can still visualize how you get to an answer from this. What you find is that when this guy is standing vertical, that you've reached this very interesting position. There it is, standing vertical. That has pushed the alpha. It's got to be quite big now. And we're saying when it's vertical, look at it now. What would happen if I push this over a little more here? This leaves the ground. And you will finish up in a situation, if you go beyond that, that you will have that one like this, and this one sitting proud of the ground and of no value. So the limiting condition for us is a right angle triangle. What are our lengths? This was 22 minus 4, which was 18. We have that bit was 5, and the long one was 30. So we do have 25 here. Sorry, I have to correct myself here. It's the full length of this. It's the whole 22 centimeters. The strap is running across here, but we have to include the 4 here and the 18 there, so it's 22. We have a right angle triangle, so we can work out alpha. It's interesting to note that the optimal, or the biggest alpha condition, wasn't very far removed from the one that we were examining beforehand, which was having 60 degrees here. Do expect in this exam to have to draw little drawings to help you figure things out. And if you have to work with your pen and your fingers, I don't care, so long as it allows you visualize. And one of the big strengths of project maths is that it does strengthen your ability to visualize. From visualizing, you find the basic little principles, and from those you can solve big problems. Last problem. A regular tetrahedron. Always watch the words. What does the word regular mean? Now you can figure out what a tetrahedron is from the drawing. What we had before was a pyramid because it had a square base. This guy has got a triangular base, so that is a tetrahedron. But what does the word regular mean? Regular is another word for, I suppose, for the classical balanced or symmetric shape. You could have this type of a tetrahedron. Where you've got a 90 degree here, and a 90 degree here, and that pointing across there. And looked at from the side, the base would be obscured. You'd have that. That's not a regular tetrahedron. If it's symmetric, you look for what axis makes it symmetric then, if it says regular. And what you expect in a regular tetrahedron is that the point is directly above the center of the base. That makes it symmetric. Okay, we've got over the wordy bit. Each, it has four faces. The one down at the underneath here, and each of the three sides. That side, the one in the back, and the one in the front here. So it does have four sides. We're going to find a piece of information out about it. Each of which is an equilateral triangle. Equilateral. Okay. A wooden puzzle consists of several pieces that can be assembled to make a regular tetrahedron. The manufacturer wants to package the assembled tetrahedron in a clear cylindrical container with one face flat against the bottom. So we know the base face of the tetrahedron is on the same plane as the base of the cylinder. If the length of one edge of the tetrahedron is 2a, now you're getting some detail. Show that the volume, that the smallest possible volume for a cylinder is this. And that is a cubed. So what do we do? Well, that's a useful piece of information. Because on any given face, whichever one you pick, let's look at the bottom one, 60, 60, 60. Look at any of these sides, any of the four sides. And we have that 60. 60, 60. That helps us find something out. We're looking for that height, for example. What's the height of our little tetrahedron? And this will be a vertical. So the first thing we've got to find out is what that length is. Whatever you want to call it, you can call it x or anything else. We know that it happens to be, I'll have to scribble, take away some of these now, that from the center out to here, we can call it the radius of the cylinder. And that happens to be exactly equal to the distance from here to any of the corners, any of the vertices of the base. We can work it out. I have an R here. I have an R here. I know I have 2A here. What's my angle there? Well, this is what we're doing now. I cut the 60 in two, so I get a 30 here, get another 30 here, And that makes this one 180 minus 2 by 30, which is 120. So I know that angle, 120 degrees. I know my length here, so I can now work out my two R's. A over root 3. Is there a problem in being able to work this out? I don't think there is, because you are doing this work in Junior Cert. In other words, the mathematics of this is very straightforward. Your problem is the one of drawing drawings to convert a small real problem, like this thing here, into a number of classical maths shapes, such as right angle triangles, isosceles triangles, or whatever, so that you can apply the basic knowledge which you have already to solve a more interesting problem. So we now know the R. Do we know the height of this? Do we know what that is? Have we been told the height of the cylindrical box? Well, all we know is they want the smallest one. That basically means that when you put the lid on here, it's just going to touch the top of the tetrahedron. We need to work out that L length here. We already have the R from here. Look at it coming out here. We want L. All the sides are 2A. That's a 2A, 2A, 2A. That's easy. I'll rewrite that. And at this stage, you're still with Junior Cert Mathematics, because you're now dealing with your cylinder. You know its radius, and you know its height. And that will work out to be that. That's the last of the questions that have been asked so far, either in the Leaving Cert or in the sample question papers that have been produced. I would like to think that this should give you confidence, because you should be able to see that the more intricate trigonometry that would have been asked in the past isn't being asked. You just have to be careful that you hear the question correctly. It's very important that the words that you use in talking in your mind about what the problem is, that those words accurately tell you what the thing is. You should just understand how words such as regular relate to things. I personally think that you should do well, because I think this is interesting maths. It's not complicated maths, and it certainly wouldn't be hard, but it's interesting. And hopefully you will find that if you are solving little problems, it's not that you will go home saying that this problem here that we're looking at, this thing of a tetrahedron inside in a cylinder, is in itself madly interesting, but it should give you a hint or an indication that the mathematics which you have already can actually get wielded by you to solve problems that are really interesting for you. Okay, I'll leave it at that. This is the trigonometry that you're to be asked, this type of stuff. You should be quite happy right now, I think. Don't go into the exam being afraid of this paper. Go into it to see what's there, to use the straightforward mathematics that you have, and you will solve the problems. So you should be happier now than before you would have started to look at what project maths really means in the exam. Okay, we'll cover more project maths the next day. Bye from Engineers Ireland.